Hello everyone. So this is week 3 and we are going to look at relational data model and normalization. For this video, we'll be discussing what we have covered in week 3. So that is only no relational data model. We will continue to look at normalization in week 4. All right. So there are two key objectives. The first key objective is to learn how to convert a entity relationship model or a extended entity relationship model to a relation model. Afterwards, we will look at how we can actually perform normalization on this relation that we have created. So the outline is basically to focus on the three types of relationship, namely unary, binary, and n-ary relationship. And the outcome is to transform all these ER diagrams into relational data model. So what is relation? A relation is a named two-dimensional table of data. So the easiest illustration is to look at the Excel spreadsheet. So basically, in the Excel spreadsheet, you will realize it's a two-dimensional table whereby you can actually have several columns. Let me just break this up right over here now. So you can imagine this is actually a relation. Okay, and it's two dimension because here you actually see the name of the column. So for example, the first one can be metric number, and the second one can be student name. Then you can have a gender, and you can have date of birth. All right. So this particular structure that I'm highlighting here is actually a relation. So a table consists of rows and columns. So basically, each of these will be a row. So for example, metric number 001, student name Ben, gender M, date of birth, let's say January 1st. Then the second student, Jaden M, and sorry, it's M, and it is 2nd of February. And finally, the third student, which is Cami, she is female and 3rd of March, for example. Okay, so here you have 3 rows. So basically, there are 3 records. So when it is a ERD, we call these instances, right? So we are saying there are 3 instances. And each of these column is each of this that we have here. So there are 4 columns. It is also called a field or a attribute in ERD. So the requirement for a table to qualify as a relation is this. First of all, it must have a unique name. So basically, this relation that we're talking about here, we can call that student relation. So that's the name. And essentially, we're just translating an entity name, which is likely also student, into a relation. Each attribute value must be atomic, meaning that there's no multi-value and not composite. In this particular illustration that we are looking at in the spreadsheet, basically it means that, for example, for student, for date of birth, it should only contain one single date of birth. In the event that there are 2 date of birth, let's say, for example, if it is this case whereby there are 2 values within this particular cell, okay, this will be a violation at atomicity. So do take note of this, and this is in fact the reason why we cannot implement multi-value attributes in a relational database, because the relation model doesn't allow this to happen. So let's delete that. Okay, then we will this will once again satisfy the atomicity principle. Every row must be unique. So basically, it is focusing on just focusing on each of these rows. Essentially, we are looking at some unique value largely. In particular, we must enforce that the primary key or the identifier in ERD, it must be unique throughout. Then in such a case, metric number can help us to uniquely identify each of the students. There must be some attributes or columns in a table, and each of those must have a unique name. So basically, we're looking at this column name. They must not be the same. They must be different. All right. And in a relation, the order of the columns must be irrelevant, meaning that we can first put metric number, or we can also implement a relation whereby metric number is last. It doesn't matter. It should work just the same. Likewise, for the sequence of these rows, currently we have Ben as the first record. It should work just the same if we have Ben as the last record, for example. Okay, so once again, a relation is essentially a set of sets. This essentially tells us that the one of the fundamental underlying theory is actually the set theory. So there's mathematics. Basically, it's a set of attributes or a set of instances. So formally, a logical data model is founded using some mathematics. We have an overall, because it is a mathematical model essentially, this relational model can be implemented on any system. So basically, its map foundation is that in terms of relation, it is actually relational algebra. Basically, that will tell us all the tables. Additionally, we can use relational algebra to explain all the operations that we can perform in all these relations. For example, select, project, join, and so on. So we will formally look at each of these operations when we look at SQL. So how does it correspond with an entity relationship diagram? As I've told you earlier, basically each relation corresponds to an entity. And of course, we should also consider all the relationships. Each row basically corresponds to an entity instance. And furthermore, columns actually corresponds to attributes. Okay, so to take very critical note, relation is not the same as relationship. Relationship is the line that links entities together in a ER model, whereas relation is something that we are trying to work out in a relational data model. So in this particular table, I'm giving you a overview in terms of the comparison or the relationship between various components, starting from the entity relationship model all the way until actual implementation on the right. That is the physical RDBMS, which stands for Relational Database Management System. So in terms of an entity, it will be implemented in a relational model as relation. Eventually, it will become a physical table in a database. Each of the instances, entity instance, become a tuple, and eventually become a record that can be inserted into the physical table. We have attributes, we have elements, and in ELD, we only focus on primary key. Remember that we discussed before that we have to underline, use a solid underline, a entity, for example, an attribute, for example, and that will indicate that it is an identifier. So effectively, it is a primary key. In the relational model, we also consider this primary key, but additionally, we'll be looking at the implementation of foreign key. The implementation of foreign key is important because that will help us to enforce the relationship between relations. And these two keys will be implemented in actual RDBMS implementation as well. So what are the differences then? If we try to compare ER and relation model, basically ER model is helpful to communicate the database design by focusing on a more conceptual level, namely just the entity and relationship and some of the attributes. Whereas a relational model helps us to address the implementation problem because of the application of relational algebra, or more directly, we'll try to apply some of the rules that is based on relational algebra. So what are the differences between relational model and table? Well, tables are ordered. So in a physical implementation in a database, we do care about the sequence in which records are being inserted into the physical table, as well as the sequence of those columns in a physical table. Whereas in a relation data model, it doesn't really matter. Tables are queried through SQL, okay, whereas relational model, we do not query it through SQL. So next on this slide, it is two slides. It's very important for us to understand the concept that are being mentioned in this slide. Essentially, we are focusing on two types of keys, namely primary keys and foreign keys. So primary keys are essentially the identifiers that we have already identified and the entity relationship diagram. So each of these identifier help us to, each of these primary key help us to uniquely identify each of the record in a table ultimately. So for example, it could be employee number, NRIC, metric number, and so on. Foreign keys are essentially identifiers that enable a dependent relation on the many side of every relationship to refer to its parent on the one side of the relationship. So basically, this means that we should have a foreign key when we have a binary relationship that is one to many. And the foreign key always sits on the many side of the relationship. So later we will be looking at some concrete examples, so we will better able to illustrate how do we actually construct foreign keys. Similar to identifier in ERD, keys can be simple, means that it is a single field. It can also be composite, that means it consists of multiple columns. Okay, so here we are looking at our very first relational schema that involves 4 relations. So basically, this involves in the ELD a customer entity that's connected to an order entity that connects to order line and that connects to product. Okay, so to better illustrate, let me try to draw that out by using our application once again. Okay, so just hang on for a second. I'm waiting for that to load out. Okay, so it is here now. So let me just very quickly draw the entity. So we have customer. Okay, we also have order. All right, and then we have a order line, which I know is an associative entity. I will tell you why very shortly. So this is order line. And then finally, product. So we have a product. Okay, and then I will have to indicate the relationship between them as well. So basically, this is the line. Okay, this is the EL model. Let me just move that up a little bit so that I can change the cardinality. Okay, so on this end, it is 1, 1 on the customer end. So the order always belongs to 1 and 1 on the customer. And a customer may have, let's say, 1 to many order. So this will be the first relationship that I would like to draw. So that links this with this. Okay. So next we will have order and product, order and order line. And order line effectively follow this as well because it is actually a associative entity. So it is 1 on this side, many on this side, and then just repeat this line again. And then we have many on this side, and then one on the other side. Okay, so now we have constructed this fairly simple EL model, and that corresponds to the example of relational schema that we have on the slide. So here you can see that there is a customer entity and a customer relation, or the entity, or the relation, and so on. Okay, I skip all the attributes just for simplicity. So let me make that slightly smaller. Okay, this is much better now. All right. Okay. So here we are saying that, as we have just mentioned, when we have a one-to-many relationship, the foreign key should sit on the many side. So we know customer comes with a primary key, which is customer ID. Okay. So this is a key. Okay. So customer ID belongs to the customer entity in the EL model. So basically I link them up. And order, we do have a primary key as well because it's underlined here. That is order ID. So once again, I draw another attribute here. That is order ID. And it is a yes again. Okay, and then I link them up as well. Okay, so how do we construct the foreign key? Basically, we know that the foreign key should sit on the many side of the relationship. That means it should sit within the order relation. Okay, and this foreign key basically is the primary key of the other side of this relationship. So in this case, it's customer, and the primary key is customer ID. So basically, this customer ID is moved over to the order side and become a foreign key. We do not need to indicate foreign key in our EL diagram. We only need to indicate primary keys, and that's why you only see this foreign key here. okay, which is the additional part that we will construct in a relational model. And we represent a foreign key using a dash underline. All right. Next, we look at this associative entity. It is an associative entity because a order will have many products. A product may also have many order, and these are many-to-many relationship. And we will perform decomposition by including an additional associative entity in between. Now, we do have a primary key for product, and in this case, it's product ID. So this is a key, and we can join them together. All right, so what happened now? Once again, we are seeing one-to-many and one-to-many relationships. So apply the logic that we have just learned when we try to handle customer and order. Basically, the primary key in the one side, which is order and hence order ID, will become the foreign key in order line because it's the many side. Likewise, product ID from the product entity will become a foreign key in order line as well. And that's why in order line in the relational model, you see these two keys, which is product ID and order ID. Now they are not they do not have dash underline, rather they have a solid underline. The reason is because they serve as primary key. It's a composite primary key in order line. Okay, so they don't just serve as foreign key, but they also at the same time serve as primary key within this relation. Okay, and the reason why we need that is because we are effectively enforcing that whenever you have a order line instance, we must have the corresponding order instance, one and one only, and concurrently the product instance, one and one only. So this is being enforced through these two keys, okay? And in constructing relational model, the indication of primary key takes precedence over foreign key, and that's why we only have the solid underline and without the dash underline. Finally, of course, is product. Okay, so that is our relational schema, and basically we are translating from this EL diagram into this relational diagram. Okay, so apart from that, we can also indicate constraints. So constraints are essentially the values that we can allow or permittable for an attribute. We must also enforce or observe entity integrity, which means that the primary key cannot be empty, and all primary key fields must have data. Okay, in other words, we only need to enforce non-null value for the primary key. All the non-key attributes actually can contain null value, including the foreign key. Okay, so the by default setting is that non-key attribute as well as foreign key attributes, they can contain null value. Of course, we can specify if we want it to be not null. Okay. The next thing that I would like to introduce to you is referential integrity, which I have highlighted in red. Effectively, this means that for any foreign key value on the relation on the many side, it must be able to match a exact instance of value on the one side of that relation. Okay, so basically it means that if we shall have an order, okay, maybe it's clearer to use this. Maybe when we have an order, we must have the respective customer ID that is responsible for this order. For example, I have 001 here, and the customer name is Ben. Order ID is 881, and it is today, and I'm the one who is ordering, so I must be able to fill up 001. Okay, let's say in this customer relation, there's just one row of customer, so it's just 001. And what happened now in the order relation is the customer ID, which is a foreign key, its value is 002. So it's pointing to no specific customer instances. Then in such a case, it's a violation of referential integrity. So it's only through referential integrity we are enforcing that whenever an order is created, we must be able to find the corresponding instance of customer through the referential integrity between these two primary key and foreign key. So effectively, we are enforcing this one-one relationship between this one-to-many relationship. All right. So if you really want to list out the details, basically we have to list out the constraint for each of the attribute. Uh, you can actually specify the size in terms of the number of characters, as well as the format of this attribute, as well as the number of digits, the amount of decimal points, and so on. So just now we talked about referential integrity. If it is required, you can actually explicitly indicate referential integrity by using this arrow. So this arrow is always built starting from the foreign key, pointing to its referencing primary key. So we do know that this customer ID is referring to this customer ID. Some of you may ask that, well, isn't it apparent that because the attribute names are actually the same, so in such a case, then they should have some primary key, foreign key relationship? Well, it's not necessary because when you have many, many relations, sometimes we might have attributes which are actually different, but they do have the same attribute name. Okay, so it is much clearer if we shall draw out the referential integrity. So for the order line relation, which is an associative entity originally, you can see that the order ID is pointing to the order ID in order, and this product ID here is pointing to the product ID in the product relation. Okay, so what are the steps that we should observe when we transform a EL diagram into a relational diagram? First of all, we must ensure that every entity becomes a table, or more specifically, become a relation. The weak entity basically takes the strong entity as part of the primary key. So we have demonstrated that when we look at the associative entity. Attributes. Basically, every attribute in the EL diagram becomes a relational attribute in the relational model. Composite attribute, okay, we only are interested in the simpler form of attributes. So for example, if you have address, which consists of street, block number, room number, as well as postal code. So in relational diagram, we will not have a address attribute. Rather, we'll have those several attributes that form up the entire address. Multi-value attributes is not allowed, so basically we have to separate these multi-value attributes into another relation altogether. So we'll look at some examples. Okay, so here is a very simple example whereby we will convert a customer entity into a relation. So the entity name basically transfer over to become a relation name, and all the attributes are transferred over accordingly, as well as the key remains as the primary key. So in this case, we see a composite attribute, which is address, and in entity diagram, you use a bracket to indicate its component of a composite attribute. So in a relational model, we are no longer interested on this composite attribute, but its underlying attribute. So you can see that actually we only consider street, city, and state, and we never consider customer address in the relational model. Here, scale in the employee entity is a multi-value attribute, meaning that there could be many, many different value of skills, multiple values of skills that's being stored within this attribute. We can't allow this to happen in relational model because that will violate atomicity principle. So what we need to do is we basically create an additional relation just for these multi-value attributes. So for employee, this entity name we transfer over to become a relation name. And the first three simple attributes are transferred over accordingly as well. Skill is now captured in the second newly created relation as an attribute. So there's skill. And employee ID is required because this skill is actually another key, which is probably some unique number as well. So 001, for example, refers to skill in SQL. 002 refers to skill in NoSQL. And employee employee 801, he has already learned both of this skill. So you will have within the relation employee skill a copy of 801 following by 001 for skill, and then a second record, which is 801 for employee ID as well. For skill, it will be 002. So this employee ID within the relation employee skill is actually a foreign key that's pointing back to the employee ID in the employee relation. And within the employee skill relation, employee ID and skill form the composite primary key. So here we are trying to transform a ER diagram into relation. So here we are looking at a dependent entity. As we have discussed earlier, we must first have employee and instance of employee, then we can create an instance of dependent. So you can imagine the father is an employee. When the father is working in this company, then we will capture the son's information. Okay, so what happened is that this is the relational model corresponding to that ER diagram in the previous slide. So employee relation is pretty simple, just a primary key and the non-key attribute. The dependent relation basically takes the keys that forms the overall dependent name. Okay, this dependent name is actually a composite attribute. So it consists of first name, middle name, and last name. So we're capturing these three components, date of birth and gender. So first name, middle name, last name, these three are the primary key, date of birth and gender. Now, additionally, to enforce that this is a dependent weak entity and the owner or the superior entity is employee, we have to implement a foreign key here. So basically, we take employee ID from employee relation and put it into dependent relation as a foreign key. And this also at the same time serves as part of the composite primary key. Okay, so in this diagram, it is all underlined, and hence these four attributes are all primary key, and we have that referential integrity to show the employee ID double up as a foreign key. So there are several different types of relationship that we can map, one to many, many to many, and one to one, optional on one side and optional on both sides. So we'll be looking at some concrete example. So here is something that we have already looked at, which is basically about customer and order. All right. In this case, we have a one to many condition. Okay, to take note of the mandatory one. Okay, because it's mandatory, we have to enforce that this foreign key will not contain null value. Okay, so we have to specify that. Otherwise, there can be null value for a foreign key. However, if it is optional one on this end, okay, we can allow for a null value for this attribute, which is the foreign key within the order relation. Okay, so here I'm showing you another way to actually represent relational model, which is here. So we just use text without drawing those boxes. So what it means is that this is the instructor relation. Within the square bracket are the attributes for this relation, or the columns for this relation. We underline the primary key as well. So for the instructor relation, we have three column, and instructor name is the primary key. And the next one is a course relation. So in this case, we have course code and course name. And we know that this is a one-to-many relationship. So the many side, we have to implement a foreign key. So we basically take the primary key from instructor and insert it into course as a foreign key. So we will use dash underline to indicate that instructor name is a foreign key. So here we see a superior entity on the left, and course semester basically is a dependent entity or weak entity that depends on course. And session, this entity again depends on course semester. So it is like two levels of dependency. So how do we implement that in relational model? First of all, we start with the owner or the superior entity. So we have course and the two column, which is C number and C name, C number being the primary key. Next, we will tackle the one in the middle, which is course semester, and we have three attributes. So we have C number, you have year, semester, and coordinator. As represented in the ELD, year, and semester are primary key for course semester. Because this is a weak dependent entity, we will take the primary key from a superior entity, which is C number. And that's why you see C number here. At the same time, it works as a primary key. So course semester has a fairly complex primary key. And finally, section. For the section relation, we should contain two attributes, which is section number and instructor. So it's section number instructor here. Since section is actually owned by course semester, so it will take whatever keys, primary keys that has been implemented in course semester. So in this case, C number, year, and semester as the primary key in section. So section is effectively has a primary key which consists of 4 columns. So here we have a many-to-many relationship, and there is an attribute that is attached to that relationship completes. So once again, basically we expect that some employee will take 0 to multiple courses, and a course can be taken by 0 to multiple employee. And if there is a pair of employee completing a course, there will be a date completed attribute that needs to be captured. We have already learned how to tackle this. Basically, we will have to conduct decomposition, and we have created this new additional entity in the middle, which is what we call certificate. So once again, employee, we have employee ID, name and date of birth. Course, we have course ID and course title, which correspond to these two entity on the left and right. In the middle is the associative entity, and in relational model, we call that associative relation. So similar to what we have done, we take the keys from employee and course, and it becomes the primary key of certificate. At the same time, each of them is actually a foreign key pointing to the owning relationship, which is the left and right. Sorry, which is the left and right. Okay, and then the attribute that is attached to the relationship will be captured in this associative relation. Okay, so here is another example whereby we have some instructor will teach 1 to 5, which is multiple courses. A course must be taught by at least one and multiple instructor. So once again, we're going to do decomposition by creating an additional associative entity in the middle. So the left and right are basically instructor and course relation, and the one in the middle is the associative relation, which has 2-column primary key, in name, and course code. So these two are, of course, also foreign keys. We can identify additional non-key attributes, for example, timetable. Okay, so here is a 1-1 optional relationship. So what we are saying here is that a nurse is in charge of 0 to multiple care center. So if a nurse is not in charge of a care center, he is just a normal nurse. And if she is in charge of a care center, then very likely she is a staff nurse. A care center is definitely being taken charge by one and only one nurse. And we would like to keep track of the date in which this relationship is assigned. So similarly, we will have to use a referential integrity, okay, to capture this relationship. Now, because this is 1-1, we do not really need to do decomposition, but we have to decide where we should actually put this data sign. So in this case, we are putting data sign at the care center. The reason is because care center is at the optional end. Okay, so whenever you see the optional end will incorporate the attribute that's attached to the relationship. Additionally, it will contain a foreign key, which points to the nurse that is being assigned to this care center. So nurse in charge is basically a nurse ID that you can find based on this nurse relation. Okay, so next we are going to look at mapping of associative entity. Basically, in the event that there's no identifier assigned to that associative entity, we will take the primary key from its left and right. If there is already an identifier assigned, then probably we do not need to do so, and it will have a simple primary key. Okay, so here we have that decomposed relationship between order and product. What we have is order line sitting in the middle. So an order may have 1 to multiple order line. When you have an order line, there's definitely a 1 and 1 only order, as well as 1 and 1 only product. A product may appear in 0 to multiple order line. So correspondingly, we can construct three relations. So order, we have order ID as the primary key. Product, if we have product ID as the primary key. And order line can capture order ID and product ID as its primary key. And at the same time, these two are also functioning as foreign key. Okay, so what happened here is, again, it is a many-to-many relationship between customer and vendor. But shipment, you can see its cardinality on this left and right is actually optionally many. Okay, so there may be many shipment, there may be none. All right. So this is the implementation when your associative entity has optional on both ends. Okay, we will still implement customer with customer ID as the primary key, vendor with vendor ID as primary key. We will still bring these two keys from its left and right to become keys within shipment, but these keys only serve as foreign key, and hence you see that referential integrity as well as dash underline. Because it's optional, we'll have to create an additional key. Sometimes we call that the surrogate key. And in this case, it's a primary key that is specific to shipment. Okay, so this is another running number within shipment. So by doing so, we may not have, well, we do not actually enforce that we have to make sure customer ID and vendor ID are actually unique within the shipment relation. Okay, so next we are going to look at some ordinary relationship. So ordinary relationship is basically recursive relationship, and that could be several forms of cardinality, one-to-many and many-to-many. Okay, so this is the first example about one-to-one relationship, and we are looking at marriage. So basically, a person marries another person. So one way to do that is we just have one single person relation, okay? And we have ID, for example, this NRIC, gender is female, date of birth 1st of January. And she is married to another guy. So this married ID basically is another instance of person. So for example, 002, gender is male, date of birth 2nd of February. So this value 2, which is the NRIC, will enter here for NRIC, which is ID as 1. Okay. The other way that we can tackle this problem is to use two relation. This approach actually allows us to keep the person relation simple. So we only have ID, gender, and date of birth, and we create a second relation which we call marries or marriage. And in this relation, we have two columns, man ID and women ID. So basically, the first one captures the husband's ID, and the second one captures the wife's ID. We only need to use one of these column as a primary key, so it can be women ID or man ID. The reason is because we only allow a man marrying a single woman. And finally, the third implementation will allow us to capture some additional information. Once again, the person relation is fairly simple, and we have a new marriage relation, and in this case, we have ID, which corresponds to a person, and also the marriage certificate. So basically, if we have person 01 and 02, 01 may have a marriage certificate that is, let's say, called 801, and 02, let's say 02 is married to 01, then 02 will also have the same value for marriage certificate as 01. Okay, so here is the employee entity, and we are interested to look at the manager relationship. So basically what we are trying to say here is that an employee can be managing 0 to multiple employees, and an employee is managed by 0 to 1 employee. So some employees are managing 0 to many, so in such a case, it is the manager, and every employee must be managed by either a manager or no manager. So in such a case, basically, we just need one single relation that captures the three attributes, and the additional column, which is what we call manager ID, that essentially points to the instance of employee that contains that manager's employee ID. So Basically, this is the first solution that we have just shown you, which is we have a employee relation with an additional foreign key, which is supervisor. The other way is to create two relation, and in such a case, we keep employee relation simple, and we have the second relation that's called supervisor. So in this supervisor relation, we have two columns. The first one is the supervisor ID. So this will capture the ID, which is from employee that belongs to that supervisor. And ID is basically those employee that this supervisor is supervising. So you can imagine if supervisor is 01, he might be supervising another employee with the ID 02 and 01, which is the second record. He is managing this another employee, which is 03, for example. The other way is to also implement an additional relation, and in this case, we have work group. So this is even more powerful because basically we can capture, for example, group number. So we can assign a group number to each of the group within the company, and who are the people, employee basically, who are assigned to this work group. And for each of these employee assigned to a work group, we can actually identify whether this is a supervisor. So each supervisor probably contains either a yes or no value, or true and false sometimes. Additionally, not just this design can capture group number for the work group, and additionally, it allows multiple supervisor within a work group. Okay, so here we have a many-to-many relationship, and is an unary relationship. So here we are essentially seeing some items that are formed based on multiple components. And these components are essentially items as well. So you can imagine we use like some screws that comes together with some other parts to form a mouse. So each of these are items, screw and button, for example, together they form a mouse. And we would like to capture the quantity of each of these items that is used to form a mouse, for example. So basically what happened is that the base relation is item. So if item number, description, and unit cost, we create a second relation that's called component. So basically it's item number, component number, and quantity. So quantity is the amount of item that goes into this contains relationship. And then both item number and component number points to item number. Okay, so component number basically means that this is a component, okay, that will form this item. Whereas item itself actually points back to item because sometimes a component directly form an item. Okay, so here are more examples on the multi-to-multi relationship. For example, if we are interested to model how a person is related to another person, first of all, we have to model the person relation. So we have the NRIC, gender, and date of birth. Then we create a second relation. In this case, we call it related to, and there are two columns, namely left ID and right ID, and the relationship type. So you can imagine relationship type could be father-son. Left ID will be the left of this relationship, so it's the father's NRIC. Right ID will be the NRIC for the son. Okay, there's another way that we can actually use to identify or to capture this relationship. Once again, we keep person relation simple, and we have the second relation that's called relationship, and in this case we capture relationship definition ID and ID, which is an NRIC, and the position. And finally, another relationship, which is what we call relationship definition, and then we have the definition of this relationship. So you can imagine that definition here, you can specify father-son, okay, and relationship ID here is 01. Okay, so this 01 basically will be used here in relationship relation. So you have 01 here. Then it's this first NRIC of this relationship pair. So you have like 801, then the position is father, and then 802, the position is son. All right. Okay, next we're going to discuss things that are slightly more complicated, which is ternary relationship. In particular, we'll pay attention to ternary relationship. Basically, we're working on the associative entity. So here is an example that we are looking at. So here you're essentially looking at a patient that is receiving, for example, some flu vaccination that's given by a physician. So you can imagine an instance of patient can be me, which is Ben. Then I'm receiving a flu jab. And the physician who is giving me this jab is Dr. Go. So all this can be captured within patient treatment. Okay, so when we implement it, you can see that the base relation, it is on top, is quite simple. So we have patient ID, patient name, so Ben and my NRIC can be captured here. Dr. Go is captured here as well as his ID, and the treatment, for example, flu jab, and that treatment code can be captured here. The associative entity, as we have indicated here, contains three attributes. So here you have the associative entity. So you have results, which is a non-key, as well as the three other attributes, which is treatment date and treatment time. Okay. And then these three on the right are essentially the keys that we take in from its respective strong entity, which is on the one side. So on the one side, we take the primary key and insert it into the many side as a key. So in this case, you have patient ID, physician ID, and treatment code from its respective relation. We draw the referential integrity because it's referring to a specific instance or record within those relations. They serve as primary key. Now, what is interesting is that we include treatment date and treatment time as the primary key of patient treatment. The reason is because, all right, I, Ben, may be receiving a flu jab that is provided by Dr. Go. However, the course of this flu jab might require me to undergo 3 treatments over 3 months' time. So in such a case, my ID is 001, physician ID is always Dr. Go's ID, and flu jab always give me this consistent same treatment code. In such a case, I will have 3 records within patient treatment with the same combination of patient ID, physician ID, and treatment code. So in other words, if we just use these 3 columns as the primary key, you will have repeating primary key, then you will have violate the principle for primary key for patient treatment. If we shall consider day and time, that will be perfectly fine because I will only take 1 treatment in a day at a particular time. So this will ensure that each of these primary key is truly unique. Sometimes we might also create a suffragate key to handle this problem. A suffragate key, as I have mentioned earlier, is an additional key that we just created it artificially to enforce uniqueness throughout this relation. Okay, so in this solution, I didn't give it a suffragate key, and I leave this as a hanging question, whether is it actually better to use a suffragate key in comparison with this complex composite primary key. So we'll come back to this problem later. Okay, so in summary, okay, in this particular discussion, we have looked at how we can transform EL diagram into relational data diagram. In particular, we look at how we can tackle unary relationship, binary relationship, as well as n-ary relationship. Thanks for watching.